project. Our next project is going to be presented by Jacob Priddle from the Queensland University of Technology. And I believe Jacob might actually have a couple extra speakers with him today in Darren Swindles and Tim Elliott. So if you could bring those in, would be great. Jacob, Darren and Tim will be speaking about from processor to farm, predictive and actionable surveillance monitoring. And so this project actually exists to increase the weight and grade of cattle at processing within supply chains by reducing the incidence of liver fluke. Now, liver fluke is a big problem in the beef industry in Australia, and it costs the industry around $100 million per annum. So Jacob, the floor is yours.
Thanks, Mick. Thanks for that kind introduction. And thank you to two of my collaborators who are here today, both Darren and Tim. They'll be sticking around at the end to answer everyone's questions, well, to help me answer the questions as well. So as Mick said, the title of this work is Predictive and Actionable Surveillance Modelling of Liver Fluke Infection. So my name is Jacob and I'm from QUT. My background is in mathematics and statistics. Before this project, I've had no knowledge about the cattle industry or liver flukes or parasites or anything like that. So it's all been very new to me. So this work, it would not be possible without all of the other people involved in the project. So we've got distinguished Professor Kerry Mengerson, also from QUT, our industry partner, Darren Swindles from Teys, Australia, Timothy Elliott from UNE, who's an expert in liver fluke, and we've also had Cameron Ralph from Food Agility. So to start off, some background information on liver fluke infection. Infection with the liver fluke parasite causes liver fluke disease, also known as fasciolosis. So the flukes burrow into the liver of the animal, causing extensive tissue damage and hemorrhaging. And the main problem with this is it causes the animal to lose their appetite, and inevitably they won't gain as much weight as the other animals, and it can also affect the quality of the meat of the animal. So liver fluke infection affects any animal that eats vegetation encysted with liver fluke cysts. So, for example, sheep, goats, and cattle. In smaller animals, infection is quite visible. They'll show many symptoms, but in larger animals like cattle, liver fluke infection is typically subclinical, with animals lacking in visible symptoms. So what this means for the farmers is that they're quite often unaware that their cattle are even infected by liver fluke. And of the farmers that are aware that liver fluke affects their cattle, they're often hesitant about investing in control measures because they don't appreciate or know or see how it actually affects the quality of the meat and the size of the animal that they have. So this leads to the two main objectives of the project, which were firstly to quantify the effect of liver fluke infection on the carcass weight and the meat quality in Australian cattle, and then in turn to estimate the economic loss to the producer for liver fluke infection. And then the second objective of the project was then to create a predictive modeling tool that can be used by farmers to estimate the risk of liver fluke infection on their property at a given time, depending on various environmental conditions. So in this talk, I'm going to focus mostly on the first objective. So for the project, we've got abattoir data provided by Teys Australia. So Teys is Australia's second largest meat processor and exporter. We have abattoir data from 6 different abattoirs collected between 2016 and 2020. So every animal processed is inspected at processing. So the health of the animal is inspected. And one of these things is an inspection of the liver, which reveals the presence or absence of liver fluke. So other variables that we've got information on are the PIC, so the property the animal was sourced from, the NIS ID, the breed of the animal. So for example, Angus, mix, or NA. Mix refers to crossbreeds of animals. We've also got the sex, the processing date, property type. So they may have come from a property, a feedlot, or a sale yard. The feed type of the animal, so grass or grain mostly, and whether or not the animal has been given growth promoting hormones. We've then also got some kind of like response variables or measures of the meat quality, such as the carcass weight, the marbling, the fat depth, the MSA index, which is a measure of the eating quality of the animal, and then a bunch of other variables that I've listed. So in table 1, I've just got the distribution of liver fluke in each of the different abattoirs. And immediately what you'll notice is that from the Wagga abattoir, 25.2% of the animals were detected to have liver fluke at processing. So this is quite a large number of animals, and it shows just how big of an issue this is. At the other abattoirs, there's quite low percentages detected, but we do have a significant amount at the Tamworth abattoir, with 4% of animals having liver fluke and 4.6 being detected to have viable liver fluke. So viable liver fluke is just like signs of actual live flukes in the liver when they're being processed, whereas liver fluke is more signs of like previous scarring from infection. So if we use the pick that each animal was sourced from, we can get an idea of the spatial distribution of liver fluke infection, and that's what I've got here. By doing this, immediately we notice that liver fluke is endemic across New South Wales and Victoria, particularly along those coastal areas. If we do the same plot for each of the different abattoirs, as shown on the right, we notice that some abattoirs that source cattle from the same regions, for example, Beenleigh and Biloela, there appears to be some kind of discrepancy in terms of the amount of liver fluke detected from the same region. And this kind of suggested to us that there may be issues or differences in the detection accuracy between different abattoirs. And so for the remainder of the analysis, we actually considered each abattoir separately. So focusing on objective 1 of the project, we wanted to estimate the effective liver fluke infection on each of these different response variables. And we've identified these variables as being of interest because they are major determinants of the price or meat quality assessment. So presumably you could address this objective by fitting a simple linear regression model with liver fluke as a predictor and adjusting for the relevant confounding variables. So for example, you might be interested in how does liver fluke affect the carcass weight, and you would have carcass weight as the response with liver fluke in there as a predictor, and then your other predictors. You may also extend it to a mixed effect model where you have a random intercept for the location the animal was sourced from. And then the estimate for beta 1 would be the estimate of the effective liver fluke on the carcass weight. So if we do this, here are some results from the Wagga abattoir. The linear model says, for example, that animals infected with liver fluke will have on average a 2.74 kilogram higher weight. So this was quite alarming for us to get this result. It's the exact opposite of what we expected. Previous researchers told us that animals infected with liver fluke will eat less and they'll end up weighing less than animals not infected. So this kind of led us to dig into this issue much deeper and to think what we could be missing or what is wrong with our current approach. So if we kind of take a step back, maybe the thing we're trying to do isn't so easy. So we're trying to identify a really small effect of liver fluke on each of these different variables across an extremely diverse and expansive data set. So there could be heaps of problems happening. So we may have selected the wrong variables to adjust for. So I wanted to emphasize that causal inference is not the same as prediction. In prediction, adding more variables will explain more variability in the response usually, resulting in better predictions. But in causal inference, if we add variables without considering the underlying relationships, then we may induce bias in that causal effect that we're interested in. So we must adjust for the relevant confounding variables, but this might be difficult because we have missing information. So we don't know which animals are treated for liver fluke, and we don't know the length and the severity of the infections. And we don't know the exact age of each animal. We could also be adjusting for the wrong variables. So this could block the effect that we're interested in. There could be problems with the model. So the model may not be flexible enough to account for interactions between variables. There could be heterogeneity in the effect of liver fluke on different subpopulations of animals. And there could also be problems with the data. So there could be selection bias in the data. So animals may only be selected for processing once they've reached a certain target weight. And this could lead to results that we were getting. There could also be potential inaccuracies in the detection of liver fluke. So by kind of drawing down a graph of the different variable interrelationships, this isn't intended to be rigorous, but just a demonstration, we can begin to identify a relevant set of adjustment variables for our model. So for example, age we must adjust for because age is a confounding variable. As age affects whether or not an animal has liver fluke, older animals are going to have a longer exposure period to the parasite and hence have a greater likelihood of being infected. At the same time, older animals are going to have a higher carcass weight because they've had more time to grow, obviously. However, we shouldn't adjust for fat depth in the model, for example, because liver fluke affects fat depth and fat depth affects the carcass weight. So if we adjust for fat depth, it's going to block the effect that we're interested in. And it would say that differences in the carcass weight are due to fat depth changing, not due to the presence or absence of liver fluke infection. And a similar thing could happen if we adjust for PIC. So the backdoor criterion can actually be applied to a directed acyclic graph to identify a relevant set of adjustment variables. And by doing this, we have identified this list of variables as adjustment variables. So HGP, feed type, property type, processing year and season, breed, sex, and age. We then shifted from the linear model to a more advanced model. So we considered a generalized random forest. So a generalized random forest is an extension of the random forest generalized to estimate any quantity identified by local moment conditions. So for treatment effect estimation, we refer to this as a causal forest. And causal forests have many attractive properties. So their ease of estimating heterogeneous treatment effects, the automated way of modeling complex variable interactions, and they've also got some tractable asymptotic theory. So just a really high level overview of how they work. A causal forest is an aggregation of estimates produced by causal trees. So each tree is grown on a random subsample of the data by recursively partitioning the feature space to minimize the mean squared error in the treatment effect, which is equivalent to maximizing heterogeneity in the treatment effect. So this is distinctly different from a regression tree where each split of the data is chosen to minimize the difference in the predicted and observed response. Here we're actually specifically targeting the differences in the treatment effect, and this makes it distinctly different from a prediction task, so like a normal random forest. And the purpose of doing this is to find groups of observations within some neighborhood, as defined by the leaves, that have a constant treatment effect, but an effect that is different from the other leaves. So we're identifying groups of animals that have the same kind of effect of liver fluke. And because of the kind of recursive nature that each tree is grown, we can use the initial splits of the data to identify groups of animals that have the greatest difference in treatment effect. So the greatest difference in the effect of liver fluke. So by doing this on the fitted generalized random forest, we actually identified that the property type and the HGP, whether or not the animals have been given HGP, have the greatest differences in the effective liver fluke, followed by the breed and the sex. So based on these results, we looked at 3 different levels of heterogeneity in the effective liver fluke infection based on combinations of these variables that we know are really important, if that makes sense. So here are some results that we have for the weight for animals processed at Wagga. So for the first level, I've got level 1, level 2, and level 3. Level 1 just is overall for all animals, what is the average effective liver fluke on the weight? And here we have that where we now estimate that the effective liver fluke is 0.44 kilograms higher weight. And this is still positive. However, if we look at that finer level of heterogeneity, so for combinations of HGP and property type, we notice that there's distinct differences in how liver fluke affects these groups of animals. So animals that are HGP false, so they haven't been given growth promotants, are negatively impacted by liver fluke. However, animals that are HGP are positively impacted. So that's what these are showing here. If we look at this at the third level of heterogeneity, so for combinations of HGP, property type, breed, and sex, we notice that there's even further substantive differences between the different breeds and also small differences between the different sex of animals. So if we focus on those HGP-free false animals sourced from properties, the blue ones here, we can see that Angus females were estimated to have a 4.66 kilogram lower weight, and Angus males had a 4.57 kilogram lower weight. On the other hand, mixed breed males had a 0.51 kilogram higher weight, and mixed breed females had a 1.36 kilogram lower weight. So this is a huge improvement from that initial result we were getting from this linear model. And we can also repeat this for each of the response variables we're interested in. Generally, we see a similar pattern with the HGP-free animals sourced from properties being the most negatively impacted for each of the different variables. We find across the board that all animals have lower fat depths if they were infected with liver fluke, and the animals were processed at an older age if they were infected with liver fluke. We can also compare the results between the abattoirs. There seems to be quite a high degree of correspondence between them. However, there's a lot more uncertainty for the results from Beanley and Narracourt due to the lower numbers of liver fluke recorded. So now that we've estimated the effective liver fluke on each of those variables, what we were really interested in doing is seeing how that affects the price that the producer is actually paid for their animals. So Teys pays the producer for their animals based on these publicly available pricing grids. So each animal is classified into a group according to all these variables here, so the teeth, the fat, etc. And then based on the group, they're assigned a price according to their weight. So then the total price paid is just the weight of the animal multiplied by the price per kilogram. So these are all prices per kilogram. So importantly, animals infected with liver fluke may not just weigh less and in turn have a lower price, but they may be assigned a lower price per kilogram, incurring an even greater cost. So what we did from there is we automated the kind of pricing table process. So we created a function in R where we can take each of those variables as inputs and then classify each observation into a group and then find the price. So each observation is classified according to the group, the highest group that they were eligible for, and to be eligible for a group, they must satisfy all of the different criteria. So this example animal failed all of these criteria for the higher groups, but satisfies all of S1, so it was classified as S1. And then based off its weight, it was 185, we can find that the price is 600 cents per kilogram for that animal. So we repeated this process for all of the different animals in the data set, and then multiplied the price per kilogram by the weight to get the total price paid. We also considered 2 additional scenarios whereby no animals have liver fluke and all animals have liver fluke. So to get to those 2 later scenarios, we had to work out the adjusted weight of the animal using that estimated effective liver fluke infection from our generalized random forest model. So for example, if the animal didn't have liver fluke, we would just subtract the like 4.5 kilograms or whatever from the weight of the animal to get the hypothetical weight if that animal was infected. And then we would reclassify that animal using the function we made to get the new price per kilogram, and then work out the new price paid from that. So after doing this, we can get an estimate of the average loss due to liver fluke for different types of animals. And for example, it was found that the average loss per Angus female with liver fluke is $35. And for Angus males, the loss is $32. So I've now got some kind of discussion points. So we found that animals sourced from feedlots were less impacted by liver fluke than animals sourced from properties. And an idea that we've been kind of floating around is compensatory growth to explain this. So when animals are inducted to a feedlot, and while they're in the feedlot, we believe that the burden of the flukes is lessened or removed. So the animals are no longer eating vegetation with the liver fluke parasites, so they're no longer ingesting more flukes. And they have an opportunity to kind of overcome the infection a bit. And so while they're in the feedlot, they can undergo a period of rapid growth where they catch up in size to their peers. So by the time the animals are processed, we no longer detect that difference in the weight that we would have expected. So we also need to do further research into the interaction between HGP and liver fluke, and then how that affects the different meat quality variables. So this was really kind of a novel finding. No one's ever really looked at the interaction between these 2 different things, so that could be quite interesting. We also found that Angus animals were more negatively impacted than the mixed breed animals. So this could be due to a potential bias caused by differences in the composition of breeds in the liver fluke and non-liver fluke groups. So for example, if the mixed breed has, yeah, that's fine. And then Angus animals may be sourced from higher risk regions. There could be external factors also affecting the results. So things like the accuracy of liver fluke detection. We've also got missing information, which could be affecting the results. So we don't have information on which animals have been treated. And based on the results, we recommend that animals that are HGP and sourced from properties for the cattle producers to carefully consider the merits of liver fluke treatment and control, especially if they reside in high-risk regions. So that's everything for today. Thank you.
Thanks, Jacob. That was a really fascinating talk, and really great to see that you sort of got right to the end there. I guess the potential loss or impact of what a liver fluke infected animal would bring back at the abattoir. And $32 and $35 per head is a significant amount of money to a lot of producers. So it's really good to see that. Yeah, I did have one question, and I couldn't help myself around the sort of spatial variability of the pick and liver fluke infections that you showed earlier on in one of the slides. Have you, I guess, from one of the issues that the picks can be quite large, the property identifier code for a particular property can be very large. Have you looked at trying to get a lower spatial resolution, or is there any desire to get to a lower or finer spatial resolution for that sort of pick related information?
Well, yeah, at the moment, Oh yeah, I didn't really talk about that much in this talk, but the other main piece of work for everyone else was creating a risk model where for each kind of postcode where a farmer can input like the age of their animal, and then based on the environmental conditions, we can get an estimate of the risk. And so at the moment, we're kind of restricted to going down to the postcode level due to just kind of privacy information about where each pick is located. So yeah, it would be better to go down to lower levels, but it's just kind of been a bit hard for this project.
Yeah, so I guess and a question coming from text just here as well, which would be good to answer. So, what's next for the liver fluke? You know, is there is there like an estimate of risk for the different areas? Is that what you're looking at going for? Like different areas, the estimate of risk per area? Is that what you're hoping to get out of this?
Yeah, that was, yeah, we have done that as well. That was that risk model that I was talking about. I didn't really focus on it in today's talk. Yeah, maybe Darren, do you have anything to add to
that? No, just that's a significant outcome for us is, it starts with identifying that in this geography at this time, your risk of infection is heightened. So that's sort of the alert part, and then the call to action is the economic, model, the opportunity costs that Jacob's taken us through.
Yeah.
So for us, those two parts is, because of where you are and at a point in time, due to the weather and the other inputs, Jacob could explain into the model, say, okay, your risk is heightened, you should do something. And the economic model says, okay, and now this is why you should do something, or, you can spend up to $35 a head and you're still at least breaking even or whatever.
Absolutely. And I guess from what you've seen within this research is that high rainfall zones is one of the biggest risk factors. And this season, obviously the whole eastern seaboard of Australia has been very wet. So potential, I guess, a larger potential for more incidences of liver fluke.
Yeah, and Jacob did find data earlier on, and obviously there is a direct relationship to water courses and areas like that. And we were even talking about soil types like free draining soil where water doesn't pool versus other soils. So that's the next level down, I guess. Yep. But to do it en masse with the millions of records that we have, we can only do it at the postcode level.
Yeah, okay.
But I agree, the value and the precision increases exponentially if we can get closer to that.
Yeah, and
define geography.
Yes, absolutely. And another question here, Darren, is, will you be advertising the findings of this particular project across the industry?
That's a question I can't answer on my own.
Okay.
But we certainly see the value in it for our own supply chain. Mm-hmm. Definitely. How it gets communicated is still to be determined.
Yep. Okay.
But there'll be levels to it, I think. The high level findings versus specific. Here's an alert for you.
Yeah, sure, absolutely. And I guess for the whole project team, there's the eureka moments and gnarly moments for this particular project. What has been your eureka moment so far?
Is this me?
Go for it, Jacob. Yep.
I think one of the big things for the stuff I talked about today was looking at the different subgroups of animals. So obviously I had no idea about like the differences in practice between feedlots and properties, and that's only come through conversations with Darren and Tim and feedlot managers. But it's clearly been really important to kind of look at these groups of animals separately in the model. And same with the whether or not animals have been given HGP as well. That was kind of something we realized a bit later down the track, but it's been really important.
For me, it's that players in the industry think that they're managing the situation, but the data shows clearly not. And I'm sure Tim would have a lot to say about the treatments out there, and what proof do we have of effectiveness of different things.
Yes.
And the point in time when it happens might not be right.
Yeah, I think that's the best bit, is actually being able to get the money and show the actual impact of the fluke in a dollars term, instead of saying parasites cause issues and we need to do something about it. When you can actually throw solid data, it's just gives you so much more confidence.
Yeah, absolutely. And I guess we have sort of come to the end of the time, but I'd just like to throw in one more thing. Is there been any gnarly issues that come out of this one, the eureka moments or gnarly issues for this particular project? Tim?
The HGP issue or the HGP result is a bit of a curveball. I just don't understand how a hormone affects a parasite. But I think that's something we've got to try and nut out and try and work out why we're seeing this effect.
Yep.
Yeah.
Absolutely. And Jacob, anything from you?
Yeah, I guess like trying to figure out just how to use the data in a meaningful way. Like we've got such a large volume of data, but we've been a bit restricted in some senses. So yeah, it's just been a long process, but I think we've got some really interesting results from it. Yeah.
Absolutely. And well, look, team, thank you very much for you all joining today's talk. And it's a really exciting project. We've got some very interesting insights and obviously things that you can't explain just yet, but it's looking at seeing how HGPs are affecting this is something that's, as you say, Tim, it's a bit of a curveball, but hopefully some interesting insights to come out at the end of it. So congratulations to the project thus far, and yeah, we're looking forward to seeing the final results at the end.
Thank you.
Thanks, Jacob, Darren, and Tim.